an atomic level view of elements and compounds. So we've talked about pure substances being divided into elements and compounds. We're going to look at each of these categories a little closer. Elements can be either atomic or molecular, and compounds can be either molecular or ionic. And where we see those differences is down on the particle level or the atomic level. Most elements exist in nature as single atoms. So those are called atomic elements. The atom is their basic unit. They're just individual atoms. Examples are given here. But there are some elements that exist as molecules. I think of these as the junior high girls of the elements. I don't know if you ever noticed in junior high, when a girl goes to the bathroom, she always takes a friend. Did you ever notice that? Someone pointed that out at an assembly when I was in junior high, and I'm like, no. Then I realized the next time I needed to use the restroom, yeah, I went with a friend. It was just so dumb. But it's like, insecure little girls. And so these are the junior high girls of the elements. And you don't see hydrogen atoms out by themselves. They always use the buddy system. There's 2 hydrogen atoms holding hands, right? And there's 2 chlorine atoms. They're forming a molecule. So molecular elements exist as molecules. There are 7 that are diatomic. Di is a prefix that means 2. So 2 atoms. And these are their formulas, H2, N2, O2, etc. And we need to memorize this little list here. There are 2 other molecular elements, phosphorus and sulfur. I'm not going to really test you on those. Phosphorus often forms a molecule of 4 atoms, and sulfur often forms a molecule of 8 atoms. They're called polyatomic because they have many atoms in their molecules. Yes?
These diatomic molecules, is that going to be true when they form compounds as well?
No. The diatomic elements are diatomic only when they're by themselves. When they form a compound, you could have 1 or 2 or 3 or whatever. They're not going to always be like that. They just don't like being alone, is how I think of it. They don't want to be alone. If I'm part of a group, if I'm part of this compound, then I'm okay. I don't need my girlfriend anymore. But if I'm off by myself, I'm going to find somebody to grab onto. So here on the periodic table, we're showing the molecular elements. So the pink ones here, the polyatomic ones, selenium does that as well. Those are just sort of for information. The important ones here are the yellow ones. What I think is cool about this is that there are 7 diatomic elements, and if you start at element number 7, they make the shape of the number 7. I don't know, I see patterns like that and I think it's really cool. But then what about hydrogen? Hydrogen's off on the corner. What? Hydrogen is the baby brother of the element family, right? What happens with the youngest child? They get away with stuff, right? You know this. There's a youngest child in my family. His name is Andrew. You're going to hear a lot about Andrew. Andrew's a character. He gets away with stuff. The older kids would have been punished. We would have taken them down if they did stuff like that. And hey, oh, isn't it cute? And we know we're doing it, but we can't stop. That's what hydrogen is. He's going to be an exception to all kinds of general rules that the other elements obey. The reason we don't do anything about it is we're old and we're tired, and we realize that it doesn't matter that much. We cared too much with the first ones. Kind of messed them up a little bit. So that's one way to remember these. You need to remember these 7 elements. I'm going to give you 2 other ways. One is Brinkelhoff. So that is someone's attempt to make a word out of the element symbols. So maybe that works for you. The other is a silly sentence, where the first letter of each word represents an element. So horses need oats for clear brown eyes. And this works really well until we get to the last one. So that's eyes. So the first letter or two of each word: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Horses need oats for clear brown eyes. Anytime one of these elements is alone, you're going to put a 2 subscript after its formula. So H2 or N2 or O2. In a compound, we don't need to do that, but when they're by themselves. And this will come up throughout the semester. Any questions? So those are the elements. Then the compounds. Molecular compounds usually formed from 2 or more covalently bonded nonmetals. So if you look at the compound formula and it's nonmetals, it's going to be a molecular compound. The basic unit of molecular compounds are molecules. So we're not trying to trick you. We're trying to make these descriptions easy to remember. A molecular compound has molecules in it. Examples: water, H2O. So we look at this and we see hydrogen and oxygen. What we want to do is identify, are these elements metals or nonmetals? So we look at the periodic table and we determine, are they to the left or to the right of the stair-step line? Oxygen's on the right, and oxygen's a nonmetal. Where's hydrogen? He's on the left with the metals. What's he doing over there? He's being a baby brother. Is hydrogen a metal? No. That's just something we have to remember. So hydrogen's a nonmetal, oxygen's a nonmetal. This is a molecular compound. Dry ice, carbon dioxide. 2 nonmetals, molecular compound. Propane, C3H8, carbon and hydrogen, both nonmetals, molecular compound. Any questions? Ionic compounds. Ionic compounds are composed of ions, just like the molecular compound was composed of molecules. You have to have a cation and an anion because you have to have opposite charges so that they attract. The cation is usually a metal. There are a couple of exceptions. The anions are usually 1 or more nonmetals. The basic unit is called the formula unit, and that's the smallest electrically neutral collection of ions. So that is equivalent to an empirical formula. We want the lowest ratio of the ions. If we look at table salt, which is sodium chloride, the formula unit is NaCl. Each sodium has a +1 charge. Each chloride ion has a -1 charge. And so the lowest ratio that will be electrically neutral, where the charges add up to 0, is going to be one of these to one of those. And so this is the formula unit. That is not a molecule, though. Here's an illustration of sodium chloride. So where's the formula unit? Well, you could pick out formula units all over the place, couldn't you? You could say, well, those two there, that's not a good color. Can you see that? You say those two are a formula unit. You could say, well, these two are a formula unit, one of each. But there's not a bond just between this green one and the purple one. There's also an attraction between this green one and the purple one on that side, and the purple one on the bottom. Just like magnets, the attractions go in multiple directions. I really should have brought in some of my kids' magnetics. You ever seen those little balls? metal balls with the sticks with the magnets on them. And they click together and you can make all kinds of cool stuff, right? Ionic compounds are a lot like magnetics building toy, where the positives and the negatives stick together, and they're just going to go on and on and on like that through the whole piece of stuff. So one salt crystal is essentially one molecule. It's just sodium chloride, sodium chloride, sodium chloride all the way through. And you can't say, oh, here's one molecule and there's another molecule. In a molecular compound like sugar, there are discrete molecules. Within the molecule, there are covalent bonds holding the atoms together. Between the molecules, there's a different type of force that we'll learn about later that's holding them together and making it be a solid. If you were to vaporize sodium chloride, which is possible, it's difficult but possible. If you were to vaporize this and put it into the gas state, you wouldn't have sodium chloride combinations. You'd have individual sodium and chloride ions. When a molecular compound is vaporized, here's an illustration of propane in the gas phase. We have individual molecules that are separated from one another. There's no ions. Question?
If you were to vaporize the NaCl, would the chlorine be diatomic or would it be?
That's a good question. If I vaporize this, would the chlorine be diatomic? It would not, because it would be an ion. So in the gas state, I should get rid of my white, you would have individual sodium ions and individual chloride ions.
That's the same if it was like in an aqueous solution too.
In an aqueous solution, yes, the sodium and the chloride ions will separate in the water and they'll go about independently. In a molecular compound, the molecules stay intact. And you might say, well, why aren't these attracted to each other in the gas state? Well, they would be if they got close enough. You have to put a lot of energy into it to get it into the gas state. There's a lot of space between the ions, and so then they can only be attracted if they get close enough. Like if you hold a magnet 2 inches from the refrigerator, is it attracted? Will it stick? No, the distance is too great. Question?
What would be the purpose of having it in the gas state?
What would be the purpose of having sodium chloride in the gas state? If you were doing something like mass spectrometry or something on it, you may need it in the gas state. It's not something that happens very much.
So, just as a rule, these ionic compounds are always going to have this structured repeating
Right.
structure, and then the molecular compounds are kind of just like independent molecules that are just kind of doing their own thing. They're not going to follow like any type of structure, like relational to each other, just within that compound.
That's a good question. The molecular compound molecules, some compounds have a repeating structure like this, and some do not. But all ionic compounds are going to have an order. Now, you can have defects in the crystal, so it may not be perfect, but most of the time it's going to follow this same arrangement. With the molecular compounds, I think the important thing is that the molecules are not connected to each other with the same bond that's holding the atoms together. It's a different type of force that we'll learn about later. Here, it's the same force between all of the ions, the same force all the way through the compound. Any other questions? Yes?
Is chlorine, when it's combined in two, is it soluble in water?
Is chlorine, as its diatomic element, soluble in water? I believe that it is to some extent. Yeah, I don't know off the top of my head really. Any other questions? Polyatomic ions. Prefixes again. Prefix poly, meaning many. Many atom ions. So these are ions that are composed of many atoms. And I made you memorize the names and formulas for a bunch of these. What these are is covalently bonded atoms. So it's a lot like a molecule that has become an ion by either gaining or losing an electron. So when we have an ionic compound such as this, NaNO3, this has sodium ions, Na+, and then the other ion is a nitrate ion. In Chem 1A, we're going to only be looking at ionic compounds that have 2 ions. There are compounds that have more, but we're going to look at ones that have 2. 1 cation and 1 anion. And we'll learn more about these later. But these, mysterious guys I made you memorize. Carbonate ion. It's got 1 carbon atom, 3 oxygen atoms. All of those atoms are covalently bonded together. And then overall, the whole thing together has 2 extra electrons, so it has a charge on it. And so that will cause it to be attracted to a calcium ion that has a positive charge. Positives and negatives attract. So at this point, we should be able to classify substances as elements or compounds, and then as atomic, molecular, or ionic. So fluorine. Is this an element or a compound? It's an element. So then to answer whether it's whether it's molecular or atomic, we have to ask ourselves, is it one of the 7? It is. So this is a molecular element. And if we were to write its formula, it would be F2. They gave you the name because if they gave you the formula, it'd be kind of a giveaway. How about N2O? Is that an element or a compound?
Molecular compound.
It's a compound. And we know that it's molecular because nitrogen and oxygen are both nonmetals. So we're not going to have any ions involved here. So this is going to be a molecular compound. Too much writing. What about silver? It's an element, so I'm not going to write these words anymore. E for element. It's not one of the 7, so it's atomic. So this is AE, atomic element. K2O, an ionic compound. We know that it's ionic because potassium is a metal. We look at the periodic table. We'll be looking at that periodic table a lot, right? It's a metal. Metal, nonmetal, ionic compound. That's ick, I see. How about Fe2O3? Ionic compound. Any questions?